So we've gone through transients for RC, that's first order transients, RC and RL. And you know how to solve when you're using your circuit solution techniques, right? I mean, anyone you want. I don't require you to use any special one. I have my own favorite source transforms and impediments usually work best. They're quickest usually. Y'all with me? So now today, what we're going to do, we're moving into an area where we have things varying but at a constant rate. In other words, the frequency of the voltage waveform will be constant. See those wall outlets right there? The voltage at those wall outlets varies with time. It varies at a rate of 60 hertz or 60 cycles per second. It's not a DC value. Y'all with me? How many know this, right? Most of the people I talk to in engineering, I assume that's evident, but I'm underscoring this fact. That's a time varying voltage. The actual wall voltage, or in general, any voltage where the frequency is at a constant is actually designated as some V of t is some peak value V0. And then it's cosine of omega t plus some phase angle. Now that's just the designation chosen by whoever does the standards in this area. It's a cosine variation. Omega is called the radian frequency, and omega is 2 pi f, where f is the frequency in hertz, or it's 1 over t, 1 over the period of the waveform, and omega is in radians per second. Are you familiar with these terms? How many are familiar with F? At least if you took physics, you should have seen F. And omega. Omega is just 2 pi times F because it's in radians, right? Now if you look here, the argument of cosine, it's omega t plus a phase angle. Well, anytime you have a cosine of something, it has to either be in degrees or it has to be in radians. Does everybody know that, class? The general way that it's, yeah.
So you have F, and then you have an arrow and something written between that and hertz. Is that it?
1 over t.
Between the arrow and hertz.
In hertz.
In hertz.
In. Just
in.
Put hertz.
What does it say? Cosine?
Cosine of omega t plus phi.
Omega t?
Are you familiar with? It looks like a W.
Oh, okay.
Y'all, how many have seen omega before? I mean, it's a very common Greek letter used to represent frequency in radians per second. I'm just trying to be exact about this. Now, go ahead. Somebody quick. What I want to say is, this is not DC, right? And it's not something that's exponentially decaying. It's repeating itself according to a cosine formulation, cosine of omega t, right? If we plotted that right here, and we're going to let phi be 0 for this case. If it's a cosine waveform of this is t, and this is v of t, then it starts at a value v0. It'll go down, it'll come up, and then it repeats itself, right? This would be considered the period t. Most of you know this, right? Period is just the length of time it takes before the signal repeats itself, right? Periods are, I mean, this is so common in physics and probably most of your engineering courses. Anyway, that's an expression for V of t. Now, if we take a look, and what I'm trying to do is lead up to something that's a real simplification, makes everything easy. No differential equation solutions using Laplace transforms. Everything becomes trivial if that voltage is what's forcing the event to occur. So let me explain this. Suppose I have a voltage source here, and I'm going to make it V0 cosine of omega t plus phi. That's my voltage, right? It's just a cosine variation, just like that one, with some phase angle thrown in there. Matter of fact, let me do it this way. I'm going to get rid of that phase angle for now to simplify this. Can you all see it in the far back, way back there? Can you see it? Very far back.
Mostly.
Now this marker's starting to fade. Let me get a different marker. See that one? Can you see it?
Okay,
Okay.
thank you.
And now I put a resistor here. Well, this isn't much better. Let me try to get rid of some of these. This is better. And I put a resistor here, R, and then I put an inductor here, L. And what I'm after is this. Okay. Well, let's just think about it for a second. Now, believe it or not, this is a very common thing, something akin to this or this itself, given as a general type of question if you go for an interview to make sure you know basic circuits. They'll ask something like this. And the physicists, they can always tell, write the differential equation and solve the Diffie-Q. Engineers, they know, aren't stupid. They're not going to have to do something like that if they know a better way. And that's what engineering is all about, showing you the simplest way to get the correct answer and yet still understand all the theory that leads to it. So for this, well, we know that's a series circuit, right? And we know the voltage here would be simply I of T times R. Do you agree with that? That's just the voltage across the resistor. Correct, class? This voltage would be what? Well, this voltage right here, V of L of T, would be L times di dt. Do you all agree with that? I'm making some obvious points here, right? Now we could write an equation and sum all the voltages around the closed loop and set them equal to 0. Before I do that, I just want you to see this. If I started here, I would get a voltage increase of V naught cosine omega t. Do you all see that? Then I would get minus I of t times R, and then minus L times di dt. How many see that? If I took those negative terms on the other side, I would get this. Go with me? That's a differential equation. Some of you know that if you had to solve it, you use Laplace transforms, wouldn't you? How many remember Laplace transforms? There are a lot of people that don't want to admit that in this class. Sure, Laplace transforms are a common method. You learned it when you had Diffie-Q. Remember? You had to use Laplace transforms to get through Diffie-Q. I mean, yeah, you can do this with what, an integration factor. You could break that up using a couple exponential terms with Euler's. And if you want to, you could really suffer, through the old method. But generally speaking, you'd beat it out with a Laplace transform. And really, that's the truth. And if you go to an employer and he gives you this, and you don't know what to do with it, then you've got to kind of give a justifications for why you didn't know, because this is very common, this right here. Now, the way we do it is not with Laplace transforms. Right? Yeah, you can, right? You can, but we don't. What we do is use something called a phasor, and I'm going to explain this. Remember, this is the thing that simplifies that and makes it trivial, all right? So now pay attention to this part. And here's how it works. This is Euler's identity, e to the j omega t, and really this could be anything, is cosine of omega t plus j times the sine of omega t. How many remember that? All right, this is basic, right? I think you get this in physics, surely get it in mathematics, I know that, and this is a standard identity. I promise you've had it. If you don't recall it, you've had it, believe me. I mean, honestly, how many remember this, Euler's identity? You at least heard it, right? You had to use it. I mean, there's 3 of them. You don't need to know this, but what is the cosine of omega t? Or just I'll leave it like this. Cosine omega t is e to the j omega t plus e to the minus j omega t over 2. Remember that one? And then what is the sine of omega t? That was e to the j omega t minus e to the minus j omega t over 2j. Do you remember these identities? One of the three you had to know. If you get one of them, you can get the others. I would remember something about that at least. Back in your recesses of your mind, you had to. I mean, if you are honest about it, you went to class at least somewhat, then you've seen this over and over again. It's the only way you can get through some of the math courses. They use these identities. Maybe they don't call them Oilers, but it's Oilers. Yeah.
What's above the E?
This is e to the j omega t.
J. I wrote I.
Well, okay, since you brought it up. We don't use I for the imaginary number symbol in electrical engineering. Any guesses why?
Current.
Yeah, we got a thing called current that already took that. All right, so we use J. It's the next letter, all right? But if you are physics-based, and I think that might be true in some of the other aspects of engineering, then I is usually the thing that represents an imaginary number. In electrical and computer engineering, and some other engineering, J is. And ME, is it I or is it J? I? AE, I or J? Still I?
I've been back and forth because I've had E's explain A.
Honestly, it's J here. It's just the imaginary number symbol. That's all it is. All right, now, I want to make sure you understand something. You see how this is really just the real portion of that e to the j omega t. Y'all see it? Now listen carefully. So here's the argument without getting into the weeds. They say this. Yeah, this will work. We can solve that. But what if, instead of this, suppose we make the actual forcing function. This is the thing over on this side that makes everything happen. It's called a forcing function. In mathematics, you're familiar with the term the forcing function? There was the natural, then the forced response to diffie q. Do you remember something like that back in the day when you had that stuff? Well, this is the thing that makes it happen. It forces the event to occur. It's the force. If I put this as e to the j omega t right here, then really, if I took, just listen, if I put this instead of this, I know the real part of this is this. Do y'all follow me? Just bear with me here. I'm trying to do my job. Is equal to L times di dt plus r times I of t. Now here's the argument without me getting into the deep math. If I can solve that equation, remember now I have what? I have two forcing functions. I have both the cosine and the sine times v and I, right? Now I've added one. But these are linear differential equations. So if I can find, I'll call this the total solution right here. If I can find I total of t, if I take the real part of that, now I get my I of t, and I'll show you why I'm saying it. I gotta just, you still don't see it yet. But if I, suppose I make this function, instead of putting that in, I put this in. Now I've got an extra j times sine of omega t times v naught in there, right? Take a look over there, correct class? But if I just take the real part of the solution for I, then in fact, I get the solution of this one. Now, here's the reason I'm saying it. The next part of the assumption, and I don't like to really spend a whole lot of time going through deep math because it really doesn't mean much to you. But now, I can make the case, and some of you know this, if the time-varying forcing function is periodic and repetitive like this is periodic, then I of t itself, right here, I of t, has to be some value I naught times e to the j of omega t, but it will possibly have a phase angle too, e to the j theta. How many are experienced with imaginary mathematics? Everybody in here should raise your hand, because according to the prerequisites, you've had math courses that have exposed you to imaginary math. Now, looking at the faces here and seeing how you think that tastes like bitter herb, I'll try to make sense of it. When you talk about imaginary numbers, they are just that. They're imaginary. They don't exist in the real world in the true sense, all right? However, if I have J, what's the fundamental definition of J anyway? ME's, definition of I. Yeah, that's right. Square root of -1. How is that rendered in so many ways? Well, do y'all remember it's rendered sometimes as e to the j 90 degrees? Isn't that j? Do you remember that one? Right? It's 1 at an angle of 90 degrees. And y'all remember how if this is the real axis and this is the imaginary axis, if we talk about e to the j theta, we're really talking about a vector that has a length of 1 at some angle theta, don't we? And the imaginary component would be here, or the j component, and the real component would be here. Y'all follow me on this, class? How many do? That's just standard. Don't look so upset, like, oh God, how dare you. All right? It's okay. This will make sense. It's not gonna blow your mind away. All right? It'll help you. So that's what this is. This is an imaginary, yeah.
I just can't read your handwriting. What do you have written on the x-axis?
Real.
Real, thank you.
And that's it's short for imaginary. Now, when you take a look at this, I mean, the theta is omega t because omega t will be an angle. Just appreciate, I'm trying to make sense of this for you. Usually what we do is we term it like this, okay? Now, here's the point I was getting at. When you have any kind of a forcing function with a linear differential equation, this is not true for nonlinear, then the solutions you're looking for I have to vary at the same frequency, all right? And that's why the solutions will have e to the j omega t in them. Y'all follow me on this, class? Let me see your hands if you do. The solutions must have the same time variation. If they don't, they can't be a solution. The second thing is they can have a phase, an e to the j theta, that is different. A lot of times they put e to the j theta here in the omega t, all right? You can do it that way. But really that phase just says it's skewed or it's not tracking exactly the actual value of the forcing function. It doesn't peak when the forcing function peaks, in other words. So that said, I'm going to show you now what happens after that little spiel. Well, if I know that, I know this is the form of the solution, right? Just watch. So now I'm going to write that differential equation. I have v naught e to the j omega t equal to L times, or I'll put R first. R times I, and I'll just call it I naught, e to the j omega t, e to the j theta, plus L. And you'll notice if this represents the function of form for I of t, when I take a derivative of this with respect to t, you see how you get the j omega out in front, people? Can you all see that in far back? How many see that, right? You take a derivative of that with respect to t, well, you bring out a j omega, right? Because if you take a derivative of e to the at with respect to t, you get a e to the at. Don't you, everyone? You all know that, right? Right? I mean, mathematics is the underpinning of engineering. This is just trivial math. Y'all with me on this? Let me at least understand that you're masks and all. All right. So this becomes L times j omega, right here, times I naught, right, times the phase e to the j theta times e to the j omega t. Do y'all follow me what I've done? I've taken a derivative of the assumed solution. With me? Now pay attention to this. How many see j omega t appears everywhere? Oh, that's nice. Why?
Cancels.
Because I got an eraser. That's right. Because I can get rid of it, right? And boy, does that simplify things. Because what's that right there? That's an algebraic equation, isn't it? Now, if I want to solve for the magnitude of IM, just listen to me and you're going to see the whole 9 yards here. I can, or better yet, forget magnitude. Now I can say that I naught E to the j theta equals what? Equals V naught, right? Over R plus j omega L. Do y'all see that? How many see that right there? Now omega is going to have a certain value. If it's 60 hertz as the frequency, then omega would be 2 times pi times 60, or 120 pi radians per second. Y'all with me, class? The reason I mentioned 60 is that's the wall. That's how fast or the frequency is for the wall voltage. It's very common, 60 hertz. Now I look here, and here's the next thing I have to do with this class. You look at that, and you're saying, well, I don't know how I get I naught and theta, how I'd separate it. Here's how. This is a complex number, but the magnitude for I naught would simply be V naught, let's assume that's a scalar, over the square root of R squared plus omega L squared. You all with me on this, class? Right? If you have a complex number, you want the magnitude, you square the real and imaginary parts and take the square root. How many understand that? Everybody? Now that's the magnitude, and if you want the angle, how do you get it? Well, here's what I'm going to say. If you look at this, I want you to just bear with me for a second. If I have something, and this is going to be A, and this is JB, you all understand that a hypotenuse would be square root of A squared plus B squared, right? You with me on that? This angle right here could be gotten from the tangent, right? The tangent of that phi would be what? Opposite, or B, over adjacent A. You with me on that? The J just indicates the axis, right? It's not part of the actual numerical value. You with me on this, class? Opposite over adjacent, right? Or the tangent is the opposite, tangent of the angle is opposite over adjacent. Y'all with me? All right, you come to here, well, what's the angle of this numerator? Well, it would be what? At the angle of, the opposite is omega L, the adjacent is R, so it would be at an angle of tangent inverse, or tan to the minus 1 of omega L over R. Are you with me on that? Right, this is going to be an angle. Take the inverse tan, you get an angle. Isn't that right, class? All right, so what am I really saying about that? Well, and I got first mentioned something about the angle. Now, if I have something, if I have like A at an angle theta, this is called polar notation, right? This is something you might have gotten in high school, right? Depending on what you've taken. Polar notation, it just says it has a length at an angle from some origin. That's all it is, with an axis embedded. It can also be written as AE to the J theta, right? And this is called exponential notation. Now it's putting the angle as an exponent in E with a J in front of it. You with me? Right, it's just another way to write it. Well, here, this angle I can put in terms of the exponential form, which is usually E to the J, and this would be tan minus 1 of omega L over R. Pardon me. Are you with me? Oh, yeah, it's E to the J. I just took that angle, stuck a J in front of it, and then raised everything to be an exponent of E. You with me, class?
What is that above R there?
Omega L, right?
Omega L.
Yeah. All right, and now, just bear with me on this. Listen.
Is the tan part of the exponent?
Has to be, right? We took everything to that power, right? Let me rewrite this so you can see it. This is really going to be E to the J tan minus 1 of omega L over R. Can you see that? Now what happens if I have this? If I have 1 over E to the J 30 degrees, and I want to take it upstairs. Do you remember what happens? the angle?
Negative.
Yeah, it'll just be what? E to the minus j 30 degrees because it inverts, right? Y'all remember that? Like 1 over e to the a is e to the minus a. This is standard basic mathematics, right? So I can go ahead and say this angle can come upstairs and it can be e to the minus j tan minus 1 of omega L over R. And this would be the angular component. This would be now I naught e to the j theta. So theta would be minus the inverse tangent of omega L over R, and the magnitude of I naught would be this. You all follow me on this, class? No, sir.
I didn't see how you got e to the j theta on the left side there.
Remember back here I said that the I has to follow this form? It has to vary as e to the j omega t, right? Remember that? It has to have a constant value. We don't know what that constant value is. We solve for that. And that value could be at a certain phase. In other words, it could be a complex quantity that's not in phase with the source. With me? That's how come. This was assumed, that's what comes out. That theta was an assumed form.
So when you brought the e to the top to, you know, the tangent to the negative, when you brought that to the top, that's why you had to add the e to the j theta on the left
Well,
side?
this is a phase angle, right? I didn't add it. I said I started with just magnitude. Then I put phase over there. I had to put phase over here. In other words, this is equated to that. Or theta is simply minus the tangent minus 1 of omega L over R. That's what I'm really saying. Got me? Don't let it scare you. This is not that bad at all. But I want you to understand something about this. This right here, I'm just doing the entirety of it so you have an appreciation that if we, and by the way, once I find this form, I didn't get to this. Once I have this, y'all see how I have a magnitude and an angle? You agree with that, class? I can get I of t that solves this differential equation in this way. Listen to me and write this down, please. I want to make sure this is absolutely clear and explicit. So once I have this I naught e to the j theta, then if I want the actual I of t, this is the actual value. It is the real part of this times e to the j omega t. Then you multiply it by j omega t. Now, the real part means you take this, whatever that is, you multiply it by e to the j omega t and take the real part. Just bear with me, it won't be bad at all. I want the real part of I naught times e to the j, and here it's omega t plus a phase angle, isn't it? I'm just showing it, and I'm just rewriting things, and I've combined the exponentials. Do you all agree? If you have e to the a times e to the b, it's equal to e to the a plus b, right?
Is that
What is the subscript for R? Yeah, what is the subscript for R?
This is the real part. It just means RE is taking the real part of 20. Go ahead.
In the line above it, the I naught e to the j, is that theta?
Yeah,
Okay.
it's supposed to be the angle.
Okay.
You with me, class? Now listen, remember how I put down Euler's identity? This e to the j, that stuff was cosine of that stuff plus j sine of that stuff? How many remember that? Right? I just put that down. The real part of this is just going to, this is the beautiful thing about this. That's going to be I naught, that's the magnitude, times cosine of omega t plus this phase angle. And that's I of t. Now let me make sense of this. And you're going to see why that's so important. So I wanted the I of t that solved it. but I'm an engineer, not a physicist or a mathematician. So I want to get it in the most straightforward way without going through a whole lot of steps. Now, I went through some of the steps to show you the easy. So what I did is assume this is the actual forcing function. I know the real part of that is the actual forcing function, right? So when I get the solution of that, the real part of that solution will be the actual solution. You're going to have to take my word on that, but that's true. So on this one, I take this, and I know the form of I, or the solutions have the same time variation, or e to the j omega t. They have a magnitude and a phase that I have to solve for. I stick that thing in here. I literally do the derivative with respect to time, and then I solve it algebraically, and I get this. Now I have the values for magnitude and angle. I take them, multiply by e to the j omega t. Remember when I cancel it first on both sides? Now I go ahead and multiply it out and take the real part, and I get this. When you see this done a few times, you're going to see it's trivial. But really what you're going to see, and I'll just cut to the chase, you're going to see inductors and capacitors become simply real, or become imaginary values of capacitive reactance or capacitive or inductive reactance, which is equivalent to imaginary resistances. And then you're going to be solving circuits the way you normally did, with just, resistors everywhere, only with imaginary values for that resistance. And you don't have to solve diffie Qs. That's the beauty. I'm going to show you this, and you'll thank me for it, because God help you if you had to solve diffie Qs from some of the circuits you'll see. All right, that was my spiel today. You're going to take the quiz. Would you do me a favor? Make sure there is at least one empty desk between you and your neighbor. If you can't find one, come up